Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be covering Lesson 6 of the Physics Summer Course. It's all about conservation of energy. I will say it's going to be one of the shorter lessons out of the 8, and the reason I know that is because conservation of energy is one of the most powerful tools we have in physics. And so what we're going to be doing today is we're going to be solving some problems that so much as a couple weeks ago would have taken a long time to solve some of these problems. But because of this new theorems that we're going to be learning today, it's going to be much, much easier. And so that's very exciting. So I give this introduction. You can read that if you want. I'm not going to right now. Instead, I want to give this ball on a table example. And so just imagine you have a ball on a table like this. Okay? Here's my ball. It's sitting on the edge of the table. It's not moving. And then someone knocks it over. And now it starts falling off. And obviously, it's going to hit the ground. And you can imagine what's going on here. You can picture this in your mind. Now, when we talk about energy, there's two kinds of energy today that we're going to be focusing on. There's potential energy and kinetic energy. Potential energy or gravitational energy is the energy when you have a height. Like, for instance, right now, I'm on my 5th floor balcony in my new apartment. And yes, that is a humble brag, but I don't care. I'm very happy with this apartment. And to one-up you guys even more, I engaged my girlfriend. That's a weird verb, but proposed? That's it. I proposed to my girlfriend last week. So now you're looking at an engaged Dan. Well, I guess if you're watching the recording, you can't see me. But, I also don't have a ring on my finger, but my girlfriend, now fiance, does. Anyways, where was I going with that?
Congratulations.
Thank you. If you want, you can give a round of applause, but only if you mute your mics. Thank you. That's not muted, but okay. Anyways, what I was trying to get at here was that we, at the top, have all potential energy. Oh, I remember now. I have potential energy because I'm on the 5th floor of my balcony. Well, I'm not on the balcony right now, but you get the picture, okay? If I'm basically a height above the ground, I have potential energy. Keep that in mind, by the way, because height is a relative term. In other words, my height could be measured from the carpet I'm sitting on right now, or it could be measured from the grass below me, which is probably 30 yards below me. So it all depends where you define your ground. I'm going to say in most examples, it's very obvious what the ground should be because the ground is the ground. It's usually not much dispute over that in these problems. Now, after it falls off the table, and this is like the moment right before it hits the ground. This is the moment before hitting the ground. In the moment before it hits the ground, it has all kinetic energy. In other words, all of the energy has been transferred from the form of potential energy to kinetic energy, which is the energy of motion, like things moving. And so, in other words, all the energy that was in, the height now got converted to moving energy. And basically, the reason why I keep saying this over and over again is because, and you can write this in this space right here, what I'm about to write. I don't have room, but I'll write it here. Energy cannot be created or destroyed. Period. Next sentence. It can only be transferred. It can only be transferred between forms. So in other words, you can start the problem with kinetic energy, or you can end it with potential energy, or you can start with a mixture of the two, kinetic and potential. And by the way, there's much more energy out there than just kinetic and potential, but those are the two we're going to be talking about today. Some other examples of energy that we will not be talking about today include chemical energy, heat, sound, friction. Basically, there's a lot more than just potential and kinetic energy. But we only have two equations that we're going to learn today, and it's those two, potential and kinetic energy. So now, going back here, I want to talk about conservative versus non-conservative forces. Because what we're going to be talking about today, if you read, the very first line, it's conservation of energy. We first need to know when energy is conserved, because, well, even though I just said energy is always conserved or it can't be created or destroyed, there's some things we need to work out here. So first we're going to make a T-chart. On the left we have conservative forces, and on the right we have non-conservative forces. And so the first thing I'm going to write for conservative, I'm going to write energy is conserved. And that basically means the total energy in the system stays the same. Now for non-conservative, I'm obviously going to write energy is not conserved. That means energy is either lost or gained. But remember, you can't really lose energy. So when I say lose energy, I'm saying it's being converted to a form that we cannot use. For instance, that's what friction does. The reason why friction is, bad in general is because you lose energy. It's not really being lost. It's being converted to heat and to sound, which we can't really use. We can't use heat and sound. I mean, technically you can. You can use heat, for instance, to warm your hands. But we're not talking about that right now. So, next thing that's different. If you have a conservative force acting on your object, we say that the path you take doesn't matter. The path you take doesn't matter. And I'll explain more about that on the next page. Then, of course, for non-conservative, the path is going to matter. And we're probably not going to talk about that until next week, because next week is all about non-conservative forces. And now to give you some examples of conservative forces that we're going to be dealing with today. They include the force of gravity, which is conservative, the number one choice. We also have normal force is going to be conservative. And the last is the spring force. Like, imagine you're playing a game of pinball, and you pull the spring back and launch the ball. That's one of the conservative forces. Basically, everything else in this class is non-conservative. So to give you some specific examples, for instance, friction is the number one offender when it comes to non-conservative. You lose energy due to friction. Another example is drag. Drag is just air resistance, which is non-conservative. And then the last one I'll say for today is a pushing/pulling force. If you push or pull an object, you are changing the amount of energy in the system. Usually you add energy to the system. But remember, the total energy overall stays the same. So what's happening when you push a box, your chemical energy, like the energy stored in your muscles and your body, gets converted into, for instance, kinetic energy. But again, we're not talking about chemical energy today. That would be way too confusing. I've never seen a question ever have to do with chemical energy in this class. So, without making it sound overly complicated than it is, these are the differences between conservative and non-conservative forces. And we're going to be dealing with conservative forces in today's lesson. We are not touching non-conservative until next week. So, with that being said, I'm assuming you all have this written down. Let's go ahead and go to the equations. So the first equation we have, UG, and I'll explain what that is. It's potential energy. And the equation is mgh. M is mass, G is gravity, 9.8, and H is the height. And we call this potential energy. You can also call it gravitational potential energy, but that's an extra word, and I clearly don't feel like writing that. The next form of energy we can have is K. K is the kinetic energy, and that equation is 1/2 mv squared, 1/2 mass times velocity squared. And this is known as, again, kinetic energy. Now, one thing I do want to write extra on the side here, potential energy, you're going to have that whenever you have a height. You're going to have potential energy whenever you have a height above the ground. Again, you get to pick the ground. And then kinetic energy, you're going to have that whenever you have a velocity, whenever something's moving. So that is the different kinds of energy we have. The last thing I'll say here is we have this concept, E total. This is the total energy in your system. And if you want the total energy in your system for today, all you need to do is add these two kinds of energy and you're going to be fine for today. So, are there any questions on any of that? Oh, right. The units of energy are the joule. Usually we just use capital J, which stands for joule. Any questions? Okay, then next. I'm going to tell you how to solve conservation of energy problems. It's a 3-step process. Step 1, you're going to pick 2 points. It's kind of like the initial and the final point, but you're going to pick 2 points in time. Step 2, you are going to write the following equation. E total at point 1 is equal to E total at point 2. And remember, you're going to have to be telling me what kind of energy you have at each point. Oh, and just as a reminder, the total energy is equal to UG plus K. It's the potential energy plus the kinetic energy. Sometimes you just have one. Sometimes you have both. Technically, you can have zero energy, but we're not going to be looking at those examples today. That's kind of weird. And then the last thing you're going to be doing is you're just going to solve that equation, and then you're done. So look at that. 3 easy steps. And unlike kinematics, kinematics had a step 1.5, which was split the vector into components. We actually don't have to do that for energy. This is the first concept all year that does not have vectors. It does not have anything that we have to split into a component, which is very nice. And you may be wondering, why doesn't it have that? The short answer is because energy is a scalar and not a vector. And if you don't know what that means, then I suggest you revisit page 1 of lesson 1 in your packets, because I explain it there. Anyways, we have the first example here. A kid throws an egg straight up with an initial speed of 15 meters per second. What is the maximum height that the egg reaches? Okay, so here's a fun fact actually. We did this almost exact same problem earlier in the year with kinematics. Literally the only difference was instead of an egg, it was a ball. But you're going to notice that we're going to solve this problem without using kinematics, and we're going to solve it a lot faster than when we needed kinematics, because conservation of energy is better than kinematics. So first, I'm just going to draw my egg. I'm assuming it starts from ground, essentially. You know what I mean? So it is going to be launched up with a speed of 15 meters per second. It's going to go up, 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 and then it reaches its maximum height, let's say right here. And I want to be solving for this height, h. So the question is, what is the maximum height that the egg reaches? So here's what I'm going to say. First step, pick 2 points. I think it makes the most logical sense to pick point 1 as the ground and point 2 when you've reached the max height, the peak height. So there's my 2 points. Step 2, I write E total at point 1 equals E total at point 2. This is where the thinking comes in. I really need to think about what kind of energy I have at both points. Who thinks they know what kind of energy I have at point 1? Is it gravitational energy, kinetic energy, or both?
I think at point 1, because we're starting at the ground, we just have the kinetic energy.
You're exactly
I think
right.
both.
Sorry, but the correct answer is only kinetic. And the reason why is because, I mean, I assume that the person's, let's just make up something. Let's say this person is like that tall or whatever. So really like they're a tiny bit above the ground. Again, since I get to choose my ground in any problem, I think it makes the most sense to choose the ground as where the guy's throwing it from. So there's my ground. And the reason I do that, by the way, is because, I mean, this is an actual 0 point I can get behind. I can understand this. This makes sense. So for that reason, I'm just going to pretend the ground is here. So that means the height is 0, and the only kind of energy I have is K, which is 1/2 mv squared. So there's my energy at point 1. Now it's time for energy at point 2. What kind of energy do I have at point 2?
At point 2, because it's like our peak height, I don't think that it's kind of like zero slope. We don't have any velocity at that point. So it's just that height, which is the gravitational potential energy.
And that is correct, because at peak height, your velocity is 0. So in other words, at point 2, it means that we only have gravitational potential energy, mgh. Now you'll notice here, I want to solve for my max height. I'm solving for height, but I don't have a mass. So I give up. I'm done. No, of course not. Notice the mass cancels out. It shows up on both sides. So in other words, it doesn't matter how heavy this thing is. If I throw it up at a speed of 15 meters per second, it's going to go the same height whether it's a bowling ball or whether it's a feather. Well, of course that's not true because of air resistance, but theoretically that's true. So that's cool. Anyways, I have 1/2 times, this is the initial velocity, it's not the 0, it's the 15, and then I'm just going to square it, and then I got to set it equal to 9.8 times the height, which is what I'm solving for. So it looks like the height is going to be equal to 1/2 times 15 squared, whatever that is, and then just divide both sides by 9.8. Plug this in your calculator, which I did earlier today, and you get 11.5 meters as your height. And you would get the exact same answer if you used kinematics, which is crazy. Crazy that there's two wildly different equations that get you the same answer. But are there any questions on number 1? Okay then. Now we're on to number 2. Number 2, we have a roller coaster. A roller coaster goes down the track as shown. What is the cart's velocity when it is 40 meters above the ground? Assume there is no friction or air resistance. Okay. So as you can tell, this cart is going to start here, goes to the low point of 10 meters, and then goes back up to some distance, looks like 40 meters above the ground. Again, the very first step is saying, pick 2 points. My 2 points I'm going to pick are this point right here and this point right here. Obviously the initial and the final. Which means, does it matter that I go to the 10 meters below? And the answer is no. I don't care about this point at all in the middle. As a matter of fact, this roller coaster, instead of going down, it could have went up and then down. It could have went straight across like that. You can even have a loop-the-loop in the middle if you really want to. It's not going to affect the final velocity at all, and that's because we're ignoring friction. This actually comes back to what I was saying earlier. Remember when I said conservative forces or the path doesn't matter? That's exactly what I meant when I said it. And what I also want to tell you is that if there was friction, let's say, the path does matter, and we'll see why next week. But anyways, a roller coaster goes down the track as shown. What is the cart's velocity? Okay. So we did step 1. We picked 2 points. Step 2, E total initial, or E total at point 1, equals E total at point 2. And now I just have to pick, well not pick, I have to figure out, I have to determine what kind of energy is at both points. What kind of energy do I have at point 1? Audience?
I think we just have gravitational potential energy because it says our velocity is 0 and our height is 100 meters.
Correct. That's correct. And then that is going to be mgh. If I want, I can plug in the numbers right now. Notice I don't know the mass. That's okay. It's probably going to cancel out. So I'll write mass times 9.8 times the height 100. And then what kind of energy do I have at point 2? Someone knew.
Will it be the same energy as in point 1?
It is the same in terms of it's going to equal it, but would you say there's kinetic, potential, or both?
Wouldn't there just be kinetic?
This time it is both. Do you know why? Because you've got a height above the ground. See that? Okay, I'm assuming you see it. Anyways, you're 40 meters above the ground.
Okay, thank you.
Yep. So E total at point 2 is 1/2 mv squared plus mgh. And filling in those numbers, again, I still don't know the mass. Probably doesn't matter. I'm solving for v this time. And then the mass is, again, probably going to cancel out. G is 9.8 and the height is 40. So with that, for like the third time I've said it today, mass cancels, which is good. Will it always cancel? That's a good question. Today, mass will always cancel. I'm just going to tell you that now. But in other problems, especially when you get to more advanced problems, that's not always the case. Just warning you now. Anyways, I have 9.8 times 100, that's 980, equals 1/2 v squared plus 9.8 times 40, that's going to give me 392. So now I'm on step 3, which is just solve for V. I'm obviously just going to do algebra, so subtract 392 from both sides. I get 588 equals 1/2 V squared. And now how do I solve for V? Well, I got to get rid of the 1/2. And I never divide by 1/2. I like to multiply by 2 instead. Multiply by both sides by 2. And now 1,176 equals V squared. Take the square root. The square root of 1,176 is 34.3 meters per second. And there's my velocity. By the way, I just want to say this because like all of my math students forget this. Whenever you take a square root, you should always do plus or minus in a math class. This is physics class, so you can ignore that rule. And you may be wondering, why is that? And the simple reason why is because I'm not going to have a negative velocity as my final answer. I just want to keep the positive number. So that's the answer for that one. Any questions? One thing I do want to show you, and let me just erase some of my work here. Well, actually, I don't have to erase anything. I'm just going to draw it up here. Basically, since point 1 and point 2 are right here, another interesting strategy I could do is I could move my ground up. As a matter of fact, I could move my ground up to here. Think about how that would impact the E total 1 equals E total 2. Now at E total 1, that changes a little bit. When I say MGH, the gravitational potential energy, the height is now, well, if that's 40 meters, then this distance would be 60 meters high. So that height is 60 meters. And now when I plug in E total 2, now since I'm on the ground, I don't have any more potential energy. It's all kinetic, 1/2 mv squared. And so if you set these two things equal to each other, you will get the exact same answer, 34.3 meters per second. I promise. Does that make sense? Any questions? Okay then, excellent. Next one, we have a graph question, because I want to show a graph question. Here is the energy versus time graph for a book falling off a table. If energy is conserved, draw the book's potential energy in the same plot as kinetic energy. So hopefully you see here that obviously kinetic energy is going up. And the reason why it's going up is because as the ball falls, it's going to pick up speed. And the reason why it looks like a parabola is because kinetic energy equals 1/2 mv squared, velocity squared, so it looks like a parabola. Now, is it important that you know that? No, that's not the important part. The important part is realizing what is the total energy in the system. Remember, the total energy in the system cannot change. And it's also not kinetic energy. Like, kinetic energy clearly increases over time, but the total energy in the system has to stay the same. So my advice to you is to figure out where the total energy is. And I'll give you a hint. It cannot be here, for instance. The reason why it can't be in the middle is because if it's the total energy, you can't go above it. Okay? So when you go above it, like K does, that's wrong. So then the logical answer then would follow that the total energy would be right there at the peak of K. And that is where the total energy is. Now, how do I know that? How do I know it's not above K? Because above K could be possible as well, right? The reason why it's not above K is because when you, what is this, a ball? A book. When the book falls off the table, the most energy you can have is when it's on the ground, right? So when it's on the ground, or at least the moment right before it hits the ground, it's all kinetic. Therefore, the total energy at that point right there is all kinetic, and therefore that's where the total energy is. So we're not done the problem yet. We haven't drawn the potential energy yet. But here's the secret. Your potential energy needs to add up to the kinetic energy to equal the total. So for instance, I know 2 points immediately. I know the first point for potential energy is this point right here. It's at 0 for the time, and it's on E total for the potential energy. And that's because the kinetic energy is 0. So 0 plus the total must equal the total. The other point I know for sure is going to be my, I guess you'd call this the time when the book hits the ground. Basically, it's the time when the kinetic energy is a maximum. That's when your potential energy is a minimum. And now I'm going to show you three potential options we have here. It's either going to be a straight line like this, it's going to be a curved line like this, or it's going to be a curved line the other way like this. Who thinks they know what the correct answer is? Top, middle, or bottom? The correct answer is...
Middle?
Oh, go ahead. I heard middle.
I think
Ranak?
it's bottom.
Okay, great. I choose the top and I'm right. Yay. So let's celebrate how I'm right. Anyways, why am I right? That's the more important question. It's because, remember, the energy has to add up to the total. So let's just make up a number. Let's say the total is 100. Just making up a number. If the total is 100 and this point right here is 20, which is lower, right? Then blue has to be 80 right there. It has to be really high. And you're going to notice it's symmetrical along the middle and they intersect right here. By the way, what's going on at that point? What's going on at that point right there? That's the point where the kinetic energy equals the potential energy. Do you notice anything special when you're actually looking at the book falling? No, you really don't. I mean, maybe you would say that's when it's, halfway to the ground. That's technically true. But yeah, it has to look like this because it has to mirror it so that at any point, the blue is going to match it to add up to the total, let's say 100 as a fake example. Are there any questions there? I know that was a confusing one. Okay, we're going to move on. And already there's only 2 questions left, so we're almost done today. A box slides down a 2-meter high hill with no friction. The box has an initial speed of 5 meters per second at the top of the hill. What is its speed at the bottom of the hill? So let me just draw a picture of this. We've got our hill here. You can envision it as a ramp. The hill is 2 meters high. The box is moving at initial speed of 5 meters per second at the top, and I want to know what its speed at the bottom. How am I going to solve this? Any ideas? So here's what I would say. I would say that first pick 2 points, like always, point 1 and point 2. The second thing I say is E total at point 1 equals E total at point 2. What kind of energy do I have at point 1?
I think we have both kinds of energies because we have height and we know that there's already a velocity.
And you would be correct. So that means I'm going to write mgh plus 1/2 mv squared. And again, if I plugged in here, which I can do, the mass, still unknown, as I said, it's going to cancel all day today, times g 9.8 times the height 2 plus 1/2 mv squared. That's the velocity at the top. So 1/2 times mass m times 5 squared. And then on the other side, E total 2, what kind of energy do I have at point 2? This one's at the bottom. Go ahead.
Yeah, I think this one's just kinetic energy.
This one is just kinetic energy. There's no more height because it hit the ground. And so 1/2 mv squared. I'm solving for that velocity. No problem. So now I would say that the mass cancels, like it always does. Starting to simplify, I can plug 9.8 times 2 plus 1/2 times 5 squared is 25. If you plug in the entire left side into your calculator, you get 32.1 equals 1/2 v squared. Again, you multiply by 2. So 64.2 equals v squared. And then you just take the square root of both sides. The velocity should be a number like a little bit higher than 8. And the answer is 8.01 meters per second. And there we go. Any questions? Okay. By the way, one thing I just want to mention is that, remember, for all the problems we're doing today, we could never have answered these questions without taking a really long time. Like, for instance, if you want to solve this question using forces, you cannot. You cannot because you don't know the angle of the ramp. Because you don't know the angle of the ramp, you can't tell me the acceleration. Because you don't know the acceleration, you can't use kinematics. Notice how conservation of energy is such a strong theorem. Basically, it makes a lot of the stuff we did before obsolete. Not everything, but a lot of the things. It makes them obsolete. And that's why conservation of energy is my favorite topic in all of physics. And it's also why next week, when we talk about work and energy, in other words, energy is not conserved, it's one of my least favorite topics because those problems are just as difficult as the ones we were looking at earlier in the year. So next week, we're back to the hard stuff. But for today, it was a nice break, wasn't it? And now the last problem of the night, number 5. If the box starts from rest and there is no friction, what is the box's speed at the bottom of the ramp in terms of m, g, h, and theta? I believe we looked at a problem like this last week, or I think it was last week. Basically, it's a problem where you want to write your answer in terms of variables. I'm telling you, when you take physics in the fall, they love asking questions like this. They love it. So here's what I'm going to do. The process did not change at all. You're going to pick 2 points, point 1 at the top, point 2 at the bottom. Step 2, E total at point 1 equals E total at point 2. And again, basically everything's the same. Since the box starts from rest, at point 1, it's what we've been doing all day. It's all gravitational energy. It's all mgh at point 1. And then at point 2, it's all kinetic energy because you're at the bottom. So 1/2 mv squared. Now most kids get here and they say, well, I don't know what to do because I don't have any numbers. And I tell you, I don't want any numbers. I want to write my answer in terms of the constants you see listed out here, m, g, h, and theta. And you can see I have m, g, h right here, and theta didn't even show up. Do you know what that means? It means the angle of the ramp does not matter at all. And that makes sense because what we said earlier was the conservation of energy, the path doesn't matter. In this case, that means the angle doesn't matter. That's cool. And so finally, if I want to solve for v, I want to solve for my velocity. First thing I do is cancel out mass again. So gh equals 1/2 v squared. Just like before, I'm going to multiply both sides by 2. So 2gh equals v squared. And then I just take the square root of both sides. And I get velocity equals the square root of 2 times g times h. And now if you want to, you can plug in any height you want, and you've got the velocity at the bottom. I'm going to circle this because it is the right answer. But I also want you to realize, I'm going to say again what I just said. And what did I just say? I said you can find the velocity now for any height. In other words, if I have, for instance, I drop a box like this and another box goes down a ramp like this, I know the speed at the bottom as long as energy is conserved, as long as there's no friction, there's no pushing or pulling forces. I know the speed at the bottom, it's root 2gh, so all you need to tell me is the height and I know the velocity. For instance, if the height is, let's just say 10, the velocity is going to be about 14 if you plug that in your calculator. So that's a very, very, very strong formula that we just discovered. And as a matter of fact, don't you wish we knew it earlier today? Because let me scroll up to the very first problem we did. That was with the throwing the egg upwards. You can use that equation here because velocity equals root 2gh. This one, you're actually using it backwards. You know the velocity is 15 equals root 2 times g times height is what you're solving for. So yeah, you can even use it to find height in this case. If you go to problem 2, I could have started from the very beginning. V equals root 2gh. And the height, it has to be the difference in height. In other words, it's not 100, it's not 40. It's the difference in height, which is 60. So you can say velocity equals root 2 times g is 9.8 times 60. And guess what answer you get? You get 34.3, which is what we said earlier when we did this the first time. And the only time you cannot use this equation is a problem like number 4. You cannot use this equation for number 4. Why not? Because you have an initial velocity right here. V equals root 2gh only works if your initial velocity is 0. So in other words, doesn't work for number 4, but it did work for the other ones today. And so with that, that concludes today's lesson. If during the homework, by the way, if you want to use this equation, you can. Just remember when you're allowed to use it and when you can't use it. And then again, next week we're going to be going over something really difficult, but we're getting very close to the end of the year. There's only 2 lessons left, lesson 7 and lesson 8. And then you will be well on your way to understanding physics, hopefully. So thank you all for joining me tonight. I hope you have a great rest of your Thursday, and I'll see you next week. Bye-bye.